Hello, welcome back. It's Monday and a new week. Let's continue reading a bit. So just follow my list. I'm going to read about the gas turbine turbofan turbojet. It's 12 noon. So let's read this. I need half a minute to get. I'm sorry for the noise. That's because this electric blower in my computer is kind of damaged, so it made noise like an old air conditioner. I'm working on to get another computer, but I need the money for bills and foods and stuff. No, I'm looking to buy some second hand, like $300-400 second hands, like the yellow papers, called the blue papers in my country Denmark.
Gas turbine. A gas turbine engine, or also known by its old name internal combustion turbine, is a type of continuous flow internal combustion engine. The main parts common to all gas turbine engines form the power-producing part, known as the gas generator or core, and are, in the direction of flow. 1. A rotating gas compressor. 2. A combustor. 3. A compressor driving turbine. Additional components have to be added to the gas generator to suit its application. Common to all is an air inlet, but with different configurations to suit the requirements of marine use, land use, or flight at speeds varying from stationary to supersonic. A propelling nozzle is added to produce thrust for flight. An extra turbine is added to drive a propeller, turboprop, or ducted fan, turbofan, to reduce fuel consumption by increasing propulsive efficiency at subsonic flight speeds. An extra turbine is also required to drive a helicopter rotor or land vehicle transmission, turboshaft, marine propeller or electrical generator, power turbine. Greater thrust-to-weight ratio for flight is achieved with the addition of an afterburner. The basic operation of the gas turbine is a Brayton cycle with air as the working fluid. Atmospheric air flows through the compressor that brings it to higher pressure. Energy is then added by spraying fuel into the air and igniting it so that the combustion generates a high-temperature flow. This high-temperature pressurized gas enters a turbine, producing a shaft work output in the process, used to drive the compressor. The unused energy comes out in the exhaust gases that can be repurposed for external work, such as directly producing thrust in a turbojet engine, or rotating a second, independent turbine, known as a power turbine, that can be connected to a fan, propeller, or electrical generator. The purpose of the gas turbine determines the design so that the most desirable split of energy between the thrust and the shaft work is achieved. The fourth step of the Brayton cycle, cooling of the working fluid, is omitted, as gas turbines are open systems that do not reuse the same air. Gas turbines are used to power aircraft, trains, ships, electrical generators, pumps, gas compressors, and tanks. Timeline of development, edit. 50. Earliest records of Hero's engine, Eolipile. It most likely served no practical purpose, and was rather more of a curiosity. Nonetheless, it demonstrated an important principle of physics that all modern turbine engines rely on. 1000. The trotting horse lamp, Chinese, Zheng, was used by the Chinese at lantern fairs as early as the Northern Song dynasty. When the lamp is lit, the heated airflow rises and drives an impeller with horse riding figures attached on it. whose shadows are then projected onto the outer screen of the lantern. 1500. The smoke jack was drawn by Leonardo da Vinci. Hot air from a fire rises through a single-stage axial turbine rotor mounted in the exhaust duct of the fireplace and turns the roasting spit by gear chain connection. 1791. A patent was given to John Barber, an Englishman, for the first true gas turbine. His invention had most of the elements present in the modern-day gas turbines. The turbine was designed to power a horseless carriage. 1894, Sir Charles Parsons patented the idea of propelling a ship with a steam turbine, and built a demonstration vessel, the Turbinia, easily the fastest vessel afloat at the time. 1899, Charles Gordon Curtis patented the first gas turbine engine in the U.S. 1900, Sanford Alexander Moss submitted a thesis on gas turbines. In 1903, Moss became an engineer for General Electric's steam turbine department in Lynn, Massachusetts. While there, he applied some of his concepts in the development of the turbocharger. 1903, a Norwegian, Egidius Selling, built the first gas turbine that was able to produce more power than needed to run its own components, which was considered an achievement in a time when knowledge about aerodynamics was limited. Using rotary compressors and turbines, it produced 11 HP. 1904, a gas turbine engine designed by Franz Stulz, based on his earlier 1873 patent application, is built and tested in Berlin. The Stulz gas turbine was too inefficient to sustain its own operation. 1906, the Omengord-Le gas turbine tested in France. This was a relatively large machine which included a 25-stage centrifugal compressor designed by Auguste Réteau and built by the Brown-Boveri Company. The gas turbine could sustain its own air compression but was too inefficient to produce useful work. 1910, Holworth gas turbine, pulse combustion, achieved 150 kilowatts, 200 HP. 1920s, the practical theory of gas flow through passages was developed into the more formal, and applicable to turbines, theory of gas flow past airfoils by R. Griffith, resulting in the publishing in 1926 of an aerodynamic theory of turbine design. Working test designs of axial turbines suitable for driving a propeller were developed by the Royal Aeronautical Establishment. 1930, having found no interest from the RAF for his idea, Frank Whittle patented the design for a centrifugal gas turbine for jet propulsion. The first successful test run of his engine occurred in England in April 1937. 1932, the Brown-Boveri Company of Switzerland starts selling axial compressor and turbine turbosets as part of the turbocharged steam-generating Velox boiler. Following the gas turbine principle, the steam evaporation tubes are arranged within the gas turbine combustion chamber. The first Velox plant was erected in Mondeville, Calvados, France. 1936, the first constant flow industrial gas turbine is commissioned by the Brown-Boveri Company and goes into service at Sun Oil's Marcus Hook refinery in Pennsylvania, U.S. 1937, working proof of concept prototype turbojet engine runs in UK, Frank Whittle's, and Germany, Hans von Heinz Heinkel Vs1. Henry Tizard secures UK government funding for further development of power jet's engine. 1939, the first 4MW utility power generation gas turbine is built by the Brown-Boveri Company for an emergency power station in Neuchâtel, Switzerland. The turbojet-powered Heinkel V178, the world's first jet aircraft, makes its first flight. 1940, Gendrasek CS1, a turboprop engine, made its first bench run. It was designed by Hungarian engineer Georgi Gendrasek, and was intended to power a Hungarian twin-engine heavy fighter, the RMI-1. 1944, the Junkers Jumo 004 engine enters full production, powering the first German military jets such as the Messerschmitt Me 262. This marks the beginning of the reign of gas turbines in the sky. 1946, National Gas Turbine Establishment formed from Power Jets and the Ray Turbine Division to bring together Whittle and Hein Constant's work. In Besnau, Switzerland, the first commercial reheated forward/recuperated unit generating 27 MW was commissioned. 1947, a Metropolitan Vickers G1, Gatrick, becomes the first marine gas turbine when it completes sea trials on the Royal Navy's M.G.B 2009 vessel. The Gatrick was an aeroderivative gas turbine based on the Metropolitan Vickers F2 jet engine. 1995, Siemens becomes the first manufacturer of large electricity-producing gas turbines to incorporate single crystal turbine blade technology into their production models, allowing higher operating temperatures and greater efficiency. 2011, Mitsubishi Heavy Industries tests the first 60% efficiency combined cycle gas turbine, the M501J, at its Takasego, Hygo, works. Theory of operation, edit. In an ideal gas turbine, gases undergo four thermodynamic processes: anisotropic compression, anisobaric, constant pressure, combustion, anisotropic expansion and isobaric heat rejection. Together, these make up the Brayton cycle, also known as the constant pressure cycle. It is distinguished from the Otto cycle, in that all the processes, compression, ignition, combustion, exhaust, occur at the same time, continuously. In a real gas turbine, mechanical energy is changed irreversibly, due to internal friction and turbulence, into pressure and thermal energy when the gas is compressed, in either a centrifugal or axial compressor. Heat is added in the combustion chamber and the specific volume of the gas increases, accompanied by a slight loss in pressure. During expansion through the stator and rotor passages in the turbine, irreversible energy transformation once again occurs. Fresh air is taken in place of the heat rejection. Air is taken in by a compressor, called a gas generator, with either an axial or centrifugal design, or a combination of the two. This air is then ducted into the combustor section, which can be of an annular, can, or canannular design. In the combustor section, roughly 70% of the air from the compressor is ducted around the combustor itself for cooling purposes. The remaining roughly 30% the air is mixed with fuel and ignited by the already burning air-fuel mixture, which then expands, producing power across the turbine. This expansion of the mixture then leaves the combustor section and has its velocity increased across the turbine section to strike the turbine blades, spinning the disc they are attached to, thus creating useful power. Of the power produced, 60 to 70% is solely used to power the gas generator. The remaining power is used to power what the engine is being used for, typically an aviation application, being thrust in a turbojet, driving the fan of a turbofan, rotor or accessory of a turbo shaft, and gear reduction and propeller of a turboprop. If the engine has a power turbine added to drive an industrial generator or a helicopter rotor, the exit pressure will be as close to the entry pressure as possible, with only enough energy left to overcome the pressure losses in the exhaust ducting and expel the exhaust. For a turboprop engine there will be a particular balance between propeller power and jet thrust, which gives the most economical operation. In a turbojet engine only enough pressure and energy is extracted from the flow to drive the compressor and other components. The remaining high-pressure gases are accelerated through a nozzle to provide a jet to propel an aircraft. The smaller the engine, the higher the rotation rate of the shaft must be to attain the required blade tip speed. Blade tip speed determines the maximum pressure ratios that can be obtained by the turbine and the compressor. This, in turn, limits the maximum power and efficiency that can be obtained by the engine. In order for tip speed to remain constant, if the diameter of a rotor is reduced by half, the rotational speed must double. For example, large jet engines operate around 10,000-25,000 rpm, while microturbines spin as fast as 500,000 rpm. Mechanically, gas turbines can be considerably less complex than reciprocating engines. Simple turbines might have one main moving part, the compressor /shaft turbine rotor assembly, with other moving parts in the fuel system. This, in turn, can translate into price. For instance, costing $10,000 for materials, the Jumo 004 proved cheaper than the Junkers 213 piston engine, which was $35,000, and needed only 375 hours of lower skill labor to complete, including manufacture, assembly, and shipping, compared to 1,400 for the BMW 801. This, however, also translated into poor efficiency and reliability. More advanced gas turbines, such as those found in modern jet engines or combined cycle power plants, may have 2 or 3 shafts, spools, hundreds of compressor and turbine blades, movable stator blades, and extensive external tubing for fuel, oil and air systems. They use temperature-resistant alloys, and are made with tight specifications requiring precision manufacture. All this often makes the construction of a simple gas turbine more complicated than a piston engine. Moreover, to reach optimum performance in modern gas turbine power plants, the gas needs to be prepared to exact fuel specifications. Fuel gas conditioning systems treat the natural gas to reach the exact fuel specification prior to entering the turbine in terms of pressure, temperature, gas composition, and the related WOG index. The primary advantage of a gas turbine engine is its power-to-weight ratio. Since significant useful work can be generated by a relatively lightweight engine, gas turbines are perfectly suited for aircraft propulsion. Thrust bearings and journal bearings are a critical part of a design. They are hydrodynamic oil bearings or oil-cooled rolling element bearings. Foil bearings are used in some small machines such as microturbines and also have strong potential for use in small gas turbines /auxiliary power units. Creep, edit. A major challenge facing turbine design, especially turbine blades, is reducing the creep that is induced by the high temperatures and stresses that are experienced during operation. Higher operating temperatures are continuously sought in order to increase efficiency, but come at the cost of higher creep rates. Several methods have therefore been employed in an attempt to achieve optimal performance while limiting creep, with the most successful ones being high-performance coatings and single-crystal superalloys. These technologies work by limiting deformation that occurs by mechanisms that can be broadly classified as dislocation glide, dislocation climb and diffusional flow. Protective coatings provide thermal insulation of the blade and offer oxidation and corrosion resistance. Thermal barrier coatings, TBCs, are often stabilized zirconium dioxide-based ceramics and oxidation/corrosion resistant coatings. Bond coats typically consist of aluminides or macrame, where M is typically Fe and /or Cr alloys. Using TBCs limits the temperature exposure of the superalloy substrate, thereby decreasing the diffusivity of the active species, typically vacancies, within the alloy and reducing dislocation and vacancy creep. It has been found that a coating of 1/200 m can decrease blade temperatures by up to 200 degrees Celsius, 392 degrees Fahrenheit. Bond coats are directly applied onto the surface of the substrate using pack carburization and serve the dual purpose of providing improved adherence for the TBC and oxidation resistance for the substrate. The L from the bond coats forms L2O3 on the TBC bond coat interface, which provides the oxidation resistance, but also results in the formation of an undesirable interdiffusion ID, zone between itself and the substrate. The oxidation resistance outweighs the drawbacks associated with the ID zone as it increases the lifetime of the blade and limits the efficiency losses caused by a buildup on the outside of the blades. Nickel-based superalloys boast improved strength and creep resistance due to their composition and resultant microstructure. The Gamma FCC nickel is alloyed with aluminum and titanium in order to precipitate a uniform dispersion of the coherent Ni3, Alt, gamma prime, gamma phases. The finely dispersed gamma precipitates impede dislocation motion and introduce a threshold stress, increasing the stress required for the onset of creep. Furthermore, gamma is an ordered L12 phase that makes it harder for dislocations to shear past it. Further refractory elements such as rhenium and ruthenium can be added in solid solution to improve creep strength. The addition of these elements reduces the diffusion of the gamma prime phase, thus preserving the fatigue resistance, strength, and creep resistance. The development of single crystal superalloys has led to significant improvements in creep resistance as well. Due to the lack of grain boundaries, single crystals eliminate cobble creep and consequently deform by fewer modes, decreasing the creep rate. Although single crystals have lower creep at high temperatures, they have significantly lower yield stresses at room temperature, where strength is determined by the Hall-Petch relationship. Care needs to be taken in order to optimize the design parameters to limit high temperature creep while not decreasing low temperature yield strength. Types, edit. Jet engines, edit. Air-breathing jet engines are gas turbines optimized to produce thrust from the exhaust gases, or from ducted fans connected to the gas turbines. Jet engines that produce thrust from the direct impulse of exhaust gases are often called turbojets. While still in service with many militaries and civilian operators, turbojets have mostly been phased out in favor of the turbofan engine due to the turbojet's low fuel efficiency and high noise. Those that generate thrust with the addition of a ducted fan are called turbofans, or, rarely, fan jets. These engines produce nearly 80% of their thrust by the ducted fan, which can be seen from the front of the engine. They come in two types, low bypass turbofan and high bypass, the difference being the amount of air moved by the fan, called bypass air. These engines offer the benefit of more thrust without extra fuel consumption. Gas turbines are also used in many liquid fuel rockets, where gas turbines are used to power a turbo pump to permit the use of lightweight, low-pressure tanks, reducing the empty weight of the rocket. Turboprop engines, edit. A turboprop engine is a turbine engine that drives an aircraft propeller using a reduction gear to translate high turbine section operating speed, often in the 10s of thousands, into low thousands necessary for efficient propeller operation. The benefit of using the turboprop engine is to take advantage of the turbine engine's high power-to-weight ratio to drive a propeller, thus allowing a more powerful, but also smaller engine to be used. Turboprop engines are used on a wide range of business aircraft such as the Pilatus PC-12, commuter aircraft such as the Beechcraft 1900, and small cargo aircraft such as the Cessna 208 Caravan or de Havilland Canada-8, and large aircraft, typically military, such as the Airbus A400M Transport, Lockheed AC-130 and the 60-year-old Tupolev Tu-95 strategic bomber. While military turboprop engines can vary, in the civilian market there are two primary engines to be found. The Pratt & Whitney Canada PT6, a free turbine turboshaft engine, and the Honeywell TPE331, a fixed turbine engine, formerly designated as the Garrett R Research 331. Aeroderivative gas turbines, edit. Aeroderivative gas turbines are generally based on existing aircraft gas turbine engines and are smaller and lighter than industrial gas turbines. Aeroderivatives are used in electrical power generation due to their ability to be shut down and handle load changes more quickly than industrial machines. They are also used in the marine industry to reduce weight. Common types include the General Electric LM2500, General Electric LM6000, and aeroderivative versions of the Pratt & Whitney PW4000 and Rolls-Royce RB211. Amateur gas turbines, edit. Increasing numbers of gas turbines are being used or even constructed by amateurs. In its most straightforward form, these are commercial turbines acquired through military surplus or scrapyard sales, then operated for display as part of the hobby of engine collecting. In its most extreme form, amateurs have even rebuilt engines beyond professional repair and then used them to compete for the land speed record. The simplest form of self-constructed gas turbine employs an automotive turbocharger as the core component. A combustion chamber is fabricated and plumbed between the compressor and turbine sections. More sophisticated turbojets are also built, where their thrust and light weight are sufficient to power large model aircraft. The Schreckling design constructs the entire engine from raw materials, including the fabrication of a centrifugal compressor wheel from plywood, epoxy and wrapped carbon fiber strands. Several small companies now manufacture small turbines and parts for the amateur. Most turbojet-powered model aircraft are now using these commercial and semi-commercial microturbines, rather than a Schreckling-like home build. Auxiliary power units, edit. Small gas turbines are used as auxiliary power units, APUs, to supply auxiliary power to larger, mobile, machines such as an aircraft, and are a turboshaft design. They supply 1. Compressed air for air cycle machine style air conditioning and ventilation. 2. Compressed air startup power for larger jet engines. 3. Mechanical, shaft, power to a gearbox to drive shafted accessories, and 4. Electrical, hydraulic and other power transmission sources to consuming devices remote from the APU. Industrial gas turbines for power generation, edit. See also, gas-fired power plant. Industrial gas turbines differ from aeronautical designs in that the frames, bearings, and blading are of heavier construction. They are also much more closely integrated with the devices they power, often an electric generator, and the secondary energy equipment that is used to recover residual energy, largely heat. They range in size from portable mobile plants to large, complex systems weighing more than 100 tons housed in purpose-built buildings. When the gas turbine is used solely for shaft power, its thermal efficiency is about 30%. However, it may be cheaper to buy electricity than to generate it. Therefore, many engines are used in CHP, combined heat and power, configurations that can be small enough to be integrated into portable container configurations. Gas turbines can be particularly efficient when waste heat from the turbine is recovered by a heat recovery steam generator, HRSG, to power a conventional steam turbine in a combined cycle configuration. The 605 MW General Electric 9HAR achieved a 62.22% efficiency rate with temperatures as high as 1,540 degrees Celsius. 2,800 degrees Fahrenheit. For 2018, GE offers its 826 MWh at over 64% efficiency in combined cycle due to advances in additive manufacturing and combustion breakthroughs, up from 63.7% in 2017 orders and on track to achieve 65% by the early 2020s. In March 2018, GE Power achieved a 63.08% gross